So today, I hope I'm going to get through superconductors. I'm going to start with topological superconductors, or just superconductors. And I hope today I'm going to get to do 0 dimensions and 1-dimensional superconductors, and give you an example of a symmetry-protected topological state here in 1 dimension that's got superconductivity and some other symmetry, which breaks the classification between non-interacting and interacting systems. It's got one classification in the non-interacting case and another classification in the interacting case. And I hope to also go through briefly topological indices for superconductors in 1 dimension, both interacting and non-interacting, and discuss properties of Majorana fermions and just a little bit. I know Professor von Alpen or Felix will talk about this in more detail, but I just hope to start off the day because I'm going to need them in my future lectures. So that's lecture number 1. Lecture number 2, I hope to do the 2-dimensional P plus IP, but more general 2-dimensional spectral Chern number C superconductors. And to show you, through different arguments, why these superconductors have vortices have a Majorana bound states in the core of a vortex that's threaded to them when the Chern number C is odd. So I'm going to do vortices and Majorana fermions at the core of the vortex, and to show you through some simplified argument that they've got non-abelian statistics, and to compute the non-abelian matrices for these vortices. So this is going to be at, a little bit at the BS level, because it's basically you can't do a very precise theory with this, but we'll get the gist of the non-abelian statistics in these systems. And what else do I want to do here? Oh, that's basically it. Oh yeah, and I want to basically show you that just by looking at Chern number C odd, you can get basically the fusion rules of the Ising TQFT, topological quantum field theory, just from thinking about the microscopics of the system. And then I want to show you, again through some BS argument, that there's a different characterization of these topological superconductors in 2 dimensions depending on where you look. If you look at the edge, they've got a Z classification. So the edge gives you this Chern number, which is the Z classification. If you look at the core of the vortex, there's a Z2 classification, depending on whether the C is odd or even. And if you look at the bulk phases that quasi-particles take upon, vortices basically take upon exchange, then you get a Z16 classification, or 16. It's more complicated than Z16, but it's called the 16-fold way. And all this you can do without any knowledge of topological quantum field theory. Now, in the 3rd lecture, what I hope to do is to start giving you the basis of axiomatic TQFT. So just introducing things like associativity and braiding, and basically just the basis of category theory, and to show you how this 16-fold way can be obtained in more detail and on a more soundproof level. In fact, I'm not going to do the 16-fold way because I'm just going to give it as a homework because it's actually kind of complicated. It's got 3 fields in it. But I'm going to do the Fibonacci anyons and the semions. So I'm going to do Fibonacci. I'm going to do semions through to semions and Fibonacci anyons, And this is probably going to take 2 lectures, so I'm going to do this explicitly through pentagon and hexagon equations, or really just the kind of basis of category theory. And then I'm going to show you through just making kind of like a leap of faith that if the S and T matrices describe a theory, then I can obtain this 16-fold way by just looking at the S and T matrices of the Ising, which we're going to compute, of the Ising TQFT. And hopefully in the last lecture, I'm going to show you sort of a similar, I'm just going to take the semyon TQFT, and I'm going to show you how to get it from microscopic principles in the Laughlin 1/2 state. So I'm going to construct so I think Joel and Nicola also spoke about Laughlin states. So I'm going to construct the Laughlin 1/2 state through a conformal field theory and show you how naturally semyons appear in that theory. So basically this is kind of like the outline of the talks. Okay, so let's start. So what I'm going to do is I want to define a topological insulator or topological superconductor, and the way I want to define them is in 2 ways. Way number 1, an insulator which is topologically non-trivial, or a superconductor which is topologically non-trivial, is a superconductor or an insulator which is not adiabatically continuable to the atomic limit. What does that mean? Well, the atomic limit I define as the limit where the chemical potential of any of the particles that you've got in the system goes to plus or minus infinity. That's the atomic limit for a superconductor. That's called the strong pairing phase, but let's think of it as the atomic limit. So I'm going to define this as the atomic limit for a superconductor, or if I think of an insulator, I'm just going to think of if I have more orbitals per site, the atomic limit is going to be just the limit in which those orbitals don't talk on different sites. So basically, you take the lattice and you move it. You make the lattice constant very large, and your wave functions don't depend on the size of, don't depend on momentum. They're basically just constant spinners, right? Is that clear? That if I make the lattice size large, then there's no hopping, nothing can happen. That's the most trivial case I can have, right?
What's the mu plus minus infinity thing?
So that's how I'm going to define the limit for a topological, that's how I'm define the limit, the atomic limit, the trivial limit for a superconductor, is the limit in which basically I just have a large chemical potential for, if I made the gap less than infinity, then the gap would have no influence on this system because mu is so large that basically the gap wouldn't do anything. Exactly. So this is kind of like my atomic limit. So that's one way to define the topologically non-trivial insulator. Topologically non-trivial insulator, not adiabatically continuable to atomic limit. And by abuse of notation, the atomic limit, I'm going to call it this in a superconductor. The second way to define a topological superconductor or insulator, which I'll use here, but which is not the same as the first way. So for all the practical purposes for these lectures is going to be, because we're talking about chiral phases mostly, in 2 dimensions, and in 1 dimension, all these states will have edge states. The second way I'm going to define a topological superconductor or insulator is a system which, with open boundary conditions, so if I put open boundary conditions, has some degrees of freedom at the edge, so has some edge states. Exhibits, that's topologically non-trivial. And if it's got some degrees of freedom at the end, invariably, with open boundary conditions, the system is going to have a degeneracy, right? So if I have, for example, if you think of just, don't even think of Majorana, Frank is going to talk about this. Think about an AKLT chain with spin degrees of freedom at the end. The spin degrees of freedom can be up or down, and the system with open boundary conditions is going to have some sort of a degeneracy. So, ground state with open boundary conditions is degenerate. And the degeneracy comes from the edge, comes from edge degrees of freedom. Most of the stuff that I'll be talking about in the first 2 lectures, if I close the boundary conditions, it will have ground state degeneracy 1. So the ground state will be non-general, just because it comes really from band picture. But the things that I'll be talking about here will have ground state degeneracy even in if I close the boundary conditions. But if I open the boundary conditions, they'll have more ground state degeneracy. In other words, so basically, So basically, a topologically non-trivial system, for the purposes of the lectures that I'm going to give, is going to be a system that exhibits edge degrees of freedom. Now, these 2 definitions are not the same. In other words, there's many insulators that can have no edge states, but at the same time are not adiabatically continuable to the atomic limit. And you have to make an asterisk, depending on what symmetries you have in the system. Adiabatic continuity is a process in which you respect all the symmetries that I impose on the system. So I'm going to impose some symmetries and then respect them. Okay, and then do adiabatic continuation. If I can continue the system to the atomic limit, then it's a trivial insulator. If I can't, it's a non-trivial insulator. Okay, so let me just start with some formalism, okay? So basically, what I want to introduce is charge conjugation. And I want to start with a simple Hamiltonian. So start with just the Hamiltonian p squared over 2m minus chemical potential. And make it a spinful system. So, put here C dagger P CP, and the Hamiltonian is just sum over these operators, sigma, sum over momentum, and sigma. Right, so this is the simplest Hamiltonian you can have. So now, obviously, I don't know I suppose everybody knows the BDG formalism, but I just want to make a quick point. Obviously, I can rewrite this Hamiltonian. This Hamiltonian's got 2 per momentum. It's got 2 degenerate eigenstates for spin up and spin down. But I can obviously rewrite this Hamiltonian in a different form. I can rewrite this Hamiltonian by making a spinner psi p, which is, Cp up, Cp down, Cp up dagger, Cp down dagger. So I can do this. Usually I can even change p to minus p, but since this is p even, I don't really care about it. And if I do this, if I write it down like this, then obviously the Hamiltonian just becomes sum over p, and here I'll have tau z times identity, p squared over 2m minus mu, and here I have psi p dagger, psi p. And the reason for this tau z, everybody knows tensor notation, right? So we're good. The reason for this tau z is, of course, that here dagger has been replaced, and you need to do of course, there's a constant here. And you need to do an anti-commutation, and you get the minus, right? So now this system, however, now it's a 4x4 system. So rather than, this was a 2x2, I had the spin here. This one is a 4x4 system, right? So what have I done? So normally this has got 4 eigenvalues. So, and I can continue like this if I want to. I can just break it up in as many as I want. So what have I done? Well, I haven't done really anything. I've just doubled my space and introduced a redundancy in the system. Because if I diagonalize the system in this case, then some annihilation operators, some creation operators are not going to be independent, obviously, because this is not an independent degree of freedom. This is the dagger of this, right? So, point is, I can just double my degrees of freedom by introducing a redundancy in the system. Now, I also want to point out that this Hamiltonian has, so I've done nothing, basically. I've just done a stupid thing. But I want to point out that this Hamiltonian has the following property. It's got a symmetry. Well, it's got many symmetries in it. It's a simple matrix. But it's got a symmetry which tells you that the symmetry is tau x times identity. And you can clearly see that it anti-commutes with this guy. Why? Because tau x and tau z are Pauli matrices, right? Tau x and tau z anti-commute. So if I call this C symmetry, which I preempt, notation is going to be charge conjugation, this C symmetry has the property that C H of P, and by H of P, I just mean the first quantized Hamiltonian. Okay, C H of P, C to the minus 1 is equal to minus H, and here I'm going to put minus P. This one doesn't really care. We have put minus P, and I'm going to put a star. This is certainly true, but with just this symmetry, I could have done with plus P and with plus star, but I'm moving, I'm looking to the future and put this symmetry. So now, what have I done here really pictorially? Well, what I've done is I had a band that looked like this. Okay, like P squared over 2m minus mu. And I took this band and I created kind of like it's, minus itself, right? Because I've got the tau z, I've created minus itself. So what can I do here? Well, to make it, so this is just a trivial thing that I've done, it's kind of stupid. But I can do something non-trivial, where I now connect things between left and right, because I've got a degeneracy here. So now I can open a gap every time you've got degeneracies. However, in order to open a gap, you need to introduce pairing terms, and those are the superconducting pairing terms, obviously. And the pairing terms will look like this. Okay, plus Hermitian conjugate. Now, this is just the simplest BDG BCS pairing. And it just tells me that I pair a state of momentum P, a spin up with a state of minus P, spin down. Is it obvious? It's obvious to everyone why I need spin for S-wave pairing. Is it obvious? Yes. Okay. Very good. Okay, and what's that? No. Okay. Okay, well, let's say I didn't have spin. Is it obvious or is it not obvious? Yeah. Let me just find the form of this matrix. So is it until I find the form of the matrix, is it obvious to everybody why I need spin? I mean, yes, no? Okay, so obviously if I don't have spin, I have CP up, C minus P, if it's spinless, dagger. And if I put S wave and sum over momentum, I can just use this as a dummy label. So I have 1/2, and this is the anti-commutator of these, and this gives me 0. So that's why for spinless, we're going to do something else. Okay, so if I introduce this gap in this notation, then the Hamiltonian is going to take another term. It's going to be the real of delta. And if I make delta complex, then this Hermitian conjugate really acts on the delta. Also, real of delta tau x times sigma y plus imaginary of delta tau y times sigma y, I think. Exactly the opposite. Okay? It doesn't really matter. All right. So this is the term that I'm adding on it, and every time it's psi dagger P here, psi P. And notice that also, obviously, this term also has the same property as this. Why? Well, again, I have momentum-independent gaps. This will change when I put P wave. And you again see that this matrix here, this matrix anti-commutes with this and this. Okay? All right. So the full Hamiltonian now. It does, yeah, you're right. It doesn't anti-commute to the last one, but the last one's got a star here.
Okay.
So it, yeah. No, you don't. So, sorry. So I said something very good. So it anti-commutes with this one, because tau y anti-commutes with this, right? And this one is real, because I have complex here. Yeah? So this one doesn't take a star. So it just anti-commutes with this one, because it's tau x here. Now, it commutes with this one, but this one has a star, has just one sigma y, so it gets a star. Right? So this equation is still satisfied. Is that? Yeah. Okay, very good. So when I say nonsense, just... Okay. Yeah, so it anti-commutes with this one, commutes with this one, but this one has a star. This one is just sigma y and tau x. That's why it did, yeah, so it all works out. Okay, so what did this do? Well, there's now introduced terms, so the Hamiltonian, will look something like delta minus delta star, and here I'll have p squared minus mu, p squared minus mu, minus p squared minus mu, minus p squared minus mu. Okay? And now what you realize is that there's no way to go back, and so I've introduced I've doubled my space. It's kind of an artificial doubling of the space. But there's no way of going back and diagonalizing the Hamiltonian in the original space. Okay? So even though I introduced a redundancy, this redundancy is necessary in order to diagonalize the Hamiltonian. Sorry, you said there's a negative sign? Yeah, I think there's a negative sign here and a negative sign here. This is, since the Hamiltonian is p squared yeah, exactly. Very good. Okay. So, very good. So now, basically, you realize that you can't go back and diagonalize this in the original basis, just made out of this, and the redundancy is needed to actually diagonalize this Hamiltonian. And we know what I've done here is, of course, I've opened a gap at the Fermi level here. Okay, and I've created a superconductor. But really, the point is that this new symmetry that I've introduced, charge conjugation, is really not a symmetry. It's a redundancy of the Hilbert space. Okay. However, you can't see that at the first single particle level. So this is point number 1. At the single particle level, which really means first quantized single particle level, which really means I take the Hamiltonian as a matrix. This Hamiltonian looks like an insulator, because I've got an insulating gap here. Looks like an insulator with some special symmetry, which is charge conjugation. This symmetry given explicitly here. The way you know is not an insulator, so it's an insulator with some special symmetry. The way you know is not an insulator, it's a superconductor, is through the form of the spinor on which it acts. But as long as I look at the single particle first quantized level, just the matrix Hamiltonian, then this just looks like an insulator with a special symmetry. Now, close to this energy, so close to the gap, the normal modes of this Hamiltonian, so if I diagonalize this Hamiltonian, are obviously almost the same amplitude linear superposition between electrons and holes. As I go far away, the influence of the gap doesn't matter anymore. Okay, so this is just what I wanted to do about the BDG formalism, I think. Okay, the other thing that is obvious here is that if I have these terms in the Hamiltonian, the more I apply these terms, so I can do perturbation theory, I can do things where I hit the Hamiltonian, where I hit some wave function with Hamiltonians or whatever I want. The point is, since the fermion number, here I have C dagger, every time I hit some wave function with this operator, I'm going to change the fermion number. Here I'm going to change it by 2, for example. And here I'm going to change it by -2. And the kinetic term doesn't change the fermion number. Okay? But the point is that fermion number is no longer a conserved quantity because this Hamiltonian changes it. That's the same thing as you break U1. But there's another conserved quantity, which is fermion parity. So the conserved quantity now is fermion parity. Okay, and you can clearly see that because the Hamiltonian, if I just act on it, on anything with it, just conserves the fermion number mod 2. Okay, so we're going to be talking about this fermion parity quite a bit. So now let me just give you a form of of charge conservation. So now let's just go deeper into the charge conjugation matrix. When I say stupid stuff like charge conservation, just correct me. Okay, so here I gave you the representation of the charge conjugation matrix, and you can see that it acts on the Hamiltonian and it gives it a star. This is a fundamental form of an anti-unitary operator, and we can find this relation here that I've given you here just by eyeballing the Hamiltonian through actually constructing the form of this operator, or how it should look in general. The charge conjugation operator is basically just an operator that sends. It's a local operator, so it sends something on site to something on the same site. So in other words, it commutes with any spatial symmetries of the system, and sends Cj, and I put a spin label sigma on it, to some linear combination where this is a matrix, Cj sigma prime dagger. So that's the fundamental symmetry that we're trying to implement here. Okay? And now this matrix has some properties. So for the purpose of the systems that we're gonna look at, charge conjugation will square to 1. And those are the realistic systems, the spinful systems, the systems we have in nature, the systems that have spin. If you've got spin-orbit coupling, charge conjugation squares to 1, time reversal squares to -1. So this matrix C has to be unitary, and that's just respecting some commutation relations. And for the purposes of what we're doing in this class, so we're looking just at spinful systems, it's also symmetric. Okay? And so these are two properties. So this is required for maintaining the commutation relations. And so the reason why this one here is unitary, but this is just a matrix. This is like this matrix. But notice that this matrix, when you act on the Hamiltonian, this is this matrix. This C is this C. Just numbers. So yeah. Well, so I'm going to derive this right now. So, but the reason why it's anti-unitary is that it acts on H and it gives you H star. So in other words, if I was to actually write it down as an operator, I would write the charge conjugation operator as this matrix times complex conjugation.
Yeah, what did the star?
Yeah, I'm going to show you right now. Just one small step for mankind. Okay, so all we have to do here is just look at the way this symmetry is implemented on a Hamiltonian. And I'm going to take a Hamiltonian to be sum over ck dagger h of k ck. And you can take this ck here to be your psi if you want to. It's the same thing. Don't get hung up on c and C can be psi if you want to. And I'm going to do this, this implies, sigma, sigma prime, sigma prime. So I need to see how the symmetry, how charge conjugation acts on the K operators. So this assumes, by the way, translational invariance and everything. Okay? And that's not hard to do. And let's try to do it correctly. So I have Ck sigma is just sum over e to the I k r, kj, Cj sigma. So now, let me just write the charge conjugation. This is an operator. I don't know how to write it, but write it like this, okay? It's an operator. Huh? Okay, yeah, fine. Fine. Okay. So I have this, right? So this just goes on to the operator. So this, and I need a 1 over n over square root of n here, etc. Okay, those will be 1 over square root of n is the number of sites in the system. The notes have all of that in. Don't worry. It's just if the strings people can do it, why can't we? So it's e to the I k j, and here I am going to have a C, this, which is just a C sigma sigma prime, C J dagger sigma prime. Okay? So I am going to this is sum over J, okay? So this is, I'm going to take this, so this is C sigma sigma prime, sum over J of this dagger. So it's C sigma, which will send this to minus, C to minus K, C of minus K dagger sigma prime. Okay? So, charge conjugation sends the operator K at sigma into operator minus K at sigma prime. So now let's see what it does to the Hamiltonian. So again, this is an operator. This is a matrix. So what it does to the Hamiltonian now, I'm requiring that the second quantized Hamiltonian commutes with this operator, which basically means that H C to the minus 1 is equal to H. Right? Okay. But this H is sum over K, CK dagger, sigma HK, sigma sigma prime, CK sigma prime. Okay? And this is sum over K, operator, CK dagger, CK to the minus 1, H, so this is sigma 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 prime, C CK sigma prime, C to the minus 1. Right, so what I've done, so this is a number, so the operator commutes with a number.
That you don't need C minus 1.
Where? Ah, yeah. Very good. Yes. Okay. So what I've done is I've just introduced a splitting of identity. Okay. So now I can add that in here because I know how they change. And the moral of the story is, I'm not going to go through it. You're going to get notes. All of this is later in the notes. But the moral of the story is the following: this changes to C. So this is at K. They all change to minus K. And it changes to C. And if you've got the matrix, this matrix C here, and you've got, so now it's that matrix, and you've got the spin index here. Okay? This is the Hamiltonian here. And this changes to C dagger of minus K sigma prime with the matrix C I think it's C star. Okay? It's anyways, it's the minus 1. It will come out to be the minus 1. Now, notice where you get the minus here from. This minus comes from the... So now you're trying to identify this side with this side. Okay? So I'm trying to identify this side with this side. But I've got certain problems. So this is h of k. But I've got certain problems. First of all, I have minus k here. And the operator. And I have k here. So the way we identify is by identifying the first quantized single particle Hamiltonian that appears by just identifying the operator. So I need to change k, minus k here to k. But since there's a dummy summation over k, I'm going to do plus, plus, and minus here. Yeah? So that's how I get the minus p here. Okay? Okay? Now, I am going to flip these because I need C dagger on this side. So that's how you get the minus here by an anti-commutation relation. That's how you get this minus. And the way you get the star is you don't actually get the star, you get the transpose. So once you flip these, so you've flipped it, but you flip the spin indices here also. So to go back to these spin indices, you see you're going to get sigma prime here. To go back to when you flip them. To go back to these, because this was C dagger, this was C. So when I flipped them, I would get sigma prime dagger here and sigma here. But I have to go to sigma prime. And the way to do this is you get this H transpose. Okay? But H is Hermitian conjugate. So H dagger is equal to H. So then this H transpose is just H star. Okay? Is that clear? I did this in my class in which you were. So you're seeing it the second time. So if it's not clear, then I'm going to go back into that grade and I will be hell to pay. Okay. So you don't get the star, you get the transpose by hermiticity. You get the H transpose is equal to H star. So that's how you get the H star. So basically now we proved that if I have some charge conjugation, and this is a matrix, a unitary matrix. I'm just going to rewrite it here. Okay? This is going to be a guiding principle of what we're looking for. Why? Because this tells you something very important. This tells you, first of all, that for every state of energy E at k, there's a state of energy minus E at minus k. Okay? That's the first thing that it tells you. And the second thing that it tells you is that a state of, if you've got a single state of energy 0, that's basically its own antiparticle. So we'll see that. And that's the Majorana. Okay? So now I want to go and do, after all this nonsense formalism, I want to do the first topological superconductor that you'll see. But again, I'm going to do some cheating. And I'm going to work on a zero-dimensional problem. Let me work on the zero-dimensional problem. So just one site. Okay? So it turns out... Okay, so I did... Anyway. So it turns out that there is a topological superconductor in... you can define one in 0 dimensions in the following way. What I'm going to do is I'm going to do one site in a magnetic field. Okay? With a pairing potential. So I'm going to add spinful. So I'm still working with spinful things, which I'm going to get rid of because I don't like spin. I'm going to get rid of them soon. So, by the way, it's clear that if I want to implement this, if I want to write this as an operator, I'm going to add complex conjugation here to make it H star, right? Okay. So, if you've got spin-orbit coupling, the fact that the charge conjugation squares to 1, that's kind of the only possibility you have. If you don't have spin-orbit coupling, so if you have SU2, so the physical situation is T squared, time reversal symmetry. I'm not going to go through this. Equals -1, but I'm sure you know it. c squared as operator equals to 1. Now, if you've got SU2 rotational symmetry, you can make a rotation of spin coordinates in which you can go to the opposite case where t squared is 1 and c squared is minus 1. Okay? But that's not a physical thing to have. So, and the situations are actually very different. Like you can, the t squared equals 1 and c squared equals minus 1 is very different than this. Okay, I just wanted to make that a side note. Okay, so I'm going to do the zero side, the one side problem. And I'm going to have a chemical potential. So since I have one side, I'm just going to do this. And I'm going to have a magnetic field. So this let's just get the right signs. As in notes, C dagger, so this have a spin index, sigma z, C dagger. And then I'm going to add a superconducting pairing, okay, which in this case is just delta C up dagger, C down dagger, plus emission conjugate. But I'm going to consider delta very, very small. Okay? And I'm going to show you that this one-side problem has two phases, depending on which phase you... Yes?
Should be the value of the anonymous term for the magnetic field.
Should be what?
You have C dagger and C dagger.
Thank you. It's all correct in the notes. Okay, no, very good. Okay. So I'm going to work in this limit. And really in this limit, the only effect of the delta term is the fact that it breaks charge symmetry. So in other words, I'm going to solve the problem by putting delta to 0. Look at the particle number, what the particle number does. But I know particle number is not a symmetry once I have delta, even however small it is. But parity is still a symmetry, even with delta. So from particle number, I'm going to go to the actual problem. So for particle number, I'm going to solve the problem with no delta. Then I'm going to go to the case where delta is non-zero, and just look at what the parity does. And this is an obvious system. And why is it obvious? Well, if mu is larger than B, what's the ground state of the system? Somebody? Really? I mean, I'm like the least threatening person ever. But I can show you. What's the ground state of the system when what is it? It's either not occupied or doubly occupied, right? What? Okay. Fine. Let's make it doubly occupied. Okay, so it's doubly occupied, right? Whatever. If mu is positive and large, it's doubly occupied. If mu is negative and large, it's not occupied. Okay, now make mu less than B. So you won't tune mu, you tune B in a real experiment. What's the ground state of the system? Singly occupied. So this has got energy minus 2 mu. And this has energy minus mu minus B. If B is larger than mu, this beats this. Yeah? So now, obviously, as I tune B, what's going to happen? Well, there's going to be a phase transition. Okay, as I tune B between the two levels. So minus 2 mu, well, actually what's going to happen is minus 2 mu rests here, and minus mu minus B comes like this, right? As a function of B. Right? Minus 2 mu is constant. Minus mu minus B is just going to go like this. And they're going to intersect at no point. Is this degeneracy stable? Normally, if I have degeneracies, they split. Is the degeneracy stable? Yes. Why? Well, the reason why it's stable, it's obviously stable if I have charge symmetry because there's a good quantum number, particle symmetry, so particle number symmetry. But even if I introduce delta, and this is the crucial point, even if I introduce delta, these are still two distinct phases of the system. Why? Because they differ by fermion parity. Okay? Okay, so that's the first thing that I wanted to point out. And actually, I don't know if Felix is going to cover it, but this is kind of like a very simple, model for what's called, it's a trivial model for what's called a Shiba state, but it gets the physics right. If you have some impurity in a superconductor and increase the strength of the impurity, there's going to be a level crossing. And this level crossing is just this, and you know that if there's a level crossing and I have a superconductor, the superconducting gap, however small, is this one. Okay? So but I know since there's got to be a level crossing because the fermion number differs, there's a magnetic impurity in a superconductor is going to trap in gap states. So that's called the Shiba state, and I don't know if Felix is going to cover it, but that's all I'm going to say about it now. Okay. So now what I want to do is I want to introduce the Majorana fermion. Right? So what I'm going to do is I'm going to take this operator. I'm going to take the operator. So imagine these operators being like complex numbers. And obviously, because C dagger is not equal to C. And obviously a complex number has got two real numbers that it's associated with. And you can put it here square root of 2 or 2 or whatever you want. Okay? And C sigma is just the dagger of this. But these are now real fermions. So a fermion for which A is equal to A dagger is called a Majorana fermion. Okay? And I think Felix is going to talk more about them. But there's a fundamental thing that I wanted to tell you about these kind of systems, and there's a topological index. So you can rewrite this Hamiltonian in terms of these fermions by just using anti-commutation relations. So basically I have a m sigma, a n sigma, okay, that's equal to 2 delta mn delta sigma prime. So what does this mean? Okay, first of all, let's back up. Using this commutation relation, so what I've done here, I've taken one side and I've expressed this sigma is for spin up and for spin down. I expressed the spin up electron as a combination of two numbers. To maintain the canonical anti-commutation relations between these, I'm going to need this relation between Majorana fermions, and each of these A operators its own conjugate. Now I can rewrite this Hamiltonian in Majorana form, and let's see what form it can get. Well, normally, if I just group these into some sort of a super index, call it L, normally I'm going to rewrite this as I, sum over M, L, some matrix AML, AM, AL. Am I going too fast? Alright, so it's just quadratic. It's obvious, right? Alright, what are the symmetries of this matrix? And this is an important thing. Once you write down into Majorana basis, this matrix is antisymmetric. Okay? And that's very easy to see by just switching these and redoing the dummy index notation. Normally, if I wrote it down in C dagger and C, I couldn't switch these because I would get C, not on the left, not C dagger. But here, as these are Majoranas, so this is kind of like a super index L. Takes 4 values. So this is a 4x4 matrix in this case. Is that clear? Okay. So if I switch these and rename the indices, I have AML is equal to ALM. Okay? And there's another condition on AML that I can get by just making this Hermitian, and this is why I put people usually put the I here. I mean, it's not needed, but people usually put the I here. And there's another condition. If you make it Hermitian, this turns to minus I. This flips. Okay? So you flip it. So H is equal to H dagger. This turns to minus I. This flips. So I have to flip it back, in which I take care of this minus sign. But this goes to its star. Sorry, there's a minus here. Okay? So I'm not going to worry about this condition, but just worry about this condition. Okay? So this is an anti-symmetric matrix. And that's very important. Why? Well, the reason why it's important is because anti-symmetric matrices have Pfaffians. And that's the topological index of the system. It basically tells you, a change in this number tells you whether there is a change in the phase of this system. It's clear that the system has two phases, yes?
So if I put the I back in the AML, since the transformation from the Fermion basis to Majorana basis is a unitary one,
Yeah.
then the whole thing, I, AML, should be in exactly the same symmetry class as the original Hamiltonian, right?
Yeah, I mean, so far this is just particle number parity. I mean, there's no other symmetry. You can just put I can obviously put I back here, but this is kind of a convention that people, I can redefine this matrix as an I. It's still going to be anti-symmetric, but it's going to, if I redefine it with an I, it's going to change this. Okay? But people put it because of, it's a nicer form. It's more explicit, and we'll see that. Okay? Just remember this. And also the Pfaffian will take some i's to some powers if you don't put it out. Anyways. Okay. So, this system's got two phases. I want to find the topological index for these two phases. So I've got like 40 more minutes, so let me just get with it. So let me just rewrite this matrix in Majorana form. So in Majorana form, in this, where this M is 1 and 2, and the index sigma, it's a 4x4 matrix, and it's got the form B minus mu, delta minus B minus mu, delta 0, and here I have the, not the Hermitian conjugate, but the minus itself. Okay? I have the minus. So it's minus B plus mu, anyways, right? Okay, so I don't need to, okay, the eigenstates of this system, the ones that I am going to need, there's 4 eigenstates of the system. I'm going to need 2 of them just to prove a point. 1/2 b minus square root of mu squared plus delta 0 squared. And of course, if I've got 1, I've got the other. So it's plus and minus this. And think of b positive. Okay? And the Pfaffian of this matrix is minus b squared plus mu squared plus delta 0 squared. Does everybody know what a Pfaffian is? Okay. So the Pfaffian is, if I have a matrix which is antisymmetric, Aij is equal to minus Aj, I am going to take the Pfaffian of Aij is A12 times A34. So by the way, this is always an even matrix, because is it clear that when I have superconductivity, and this will use, I want you guys to keep in mind that this Hamiltonian is always an even by even matrix. Because I take C and I put C dagger in, I always double it. That's important for the vortex problem that we're going to do before. The Pfaffian of Aij is A12, A34, A56. You go like this, so that's the first term. And then you notice that this is antisymmetric in 1, 2, and 3, 4, and 5, 6, but for example, it's not antisymmetric in 2, 3. It's not antisymmetric in 2, 4. So you just antisymmetrize in all the indices that are not already antisymmetric. Okay? Is it clear how to construct the Pfaffian?
Sure. Can you give an example on the 2x2 matrix?
So on a 2x2 matrix is just A12. No, but it's a good example. On a 4x4 matrix, it's a, so you just So let me just do it. Okay, so that's now I want to anti-symmetrize, say, 1 and 3. So A32, A32, A14. And then you want to anti-symmetrize, so I anti-symmetrize 1 and 3. I'm now going to anti-symmetrize 1 and 4 minus A42, A3, 1. And I claim that if you take out all the other ones, you've already got it, I think.
And there's no normalization?
Well, I'm going to take the sign of the Pfaffian. Okay? So
is there a relation to determinant?
yes, that's the point. So I claim that this is the index. This is the topological index. And you can obviously see it here. If b squared becomes larger or smaller than mu squared, that's the delta zero. Delta, the gap is very small, so let's forget about it in that simple model. Then this Pfaffian changes sign. So it will tell you whether you're in one phase or the other. Yeah? Is that clear?
Yes.
Okay. So why is that? Why is that true? Why is the Pfaffian a good index? Well, in this simple model, there's a following property of the Pfaffian of a matrix. Pfaffian of matrix A squared is equal to the determinant of the matrix A. Okay? Now what happens, the determinant of A just gives you the product of the eigenvalues of the Hamiltonian, right? So what happens when two levels cross, and since it's a superconductor, two levels have to cross at energy 0. What happens to the determinant? It goes to 0. Yeah? Because it's the product of eigenvalues. So it goes to 0, but unfortunately, since the levels, when they cross, if you've got a superconductor, they cross like this, the product of the eigenvalues, E and minus E, here and here, is the same. Right? Because you've got the determinant, so this is just the product of the eigenvalues. So the determinant is not sensitive to a phase transition. I mean, it tells you if the determinant goes through 0, or is 0, it tells you there's a phase transition. So, for example, here, the determinant is 0. But it's not sensitive. However, the Pfaffian, which is basically like the square root of the determinant, is sensitive to a phase transition. And the reason for it is that if you project into these low bands, say the two low-lying bands that cause the phase transition, here, there's these two bands, for example, that cause the phase transition, then the Pfaffian, the sign of the Pfaffian, is just the sign of this energy. So the sign of the Pfaffian of A is basically like taking the square root of the determinant. So this is sensitive to a phase transition, as you can see through this explicit example. And it tells you that if this is states with plus and minus, sign of the Pfaffian have to have gone through a phase transition. Okay? And you can clearly see that there is a phase transition when Pfaffian changes sign, because Pfaffian squared is equal to the determinant. Okay, so that's one thing that I wanted to show you. And we'll come back to this, because this Pfaffian index is also the index that gives that tells you whether you have a topological phase or not in one dimension. Here, topological phase or not topological phase is kind of a useless meaning, because I just have one side. The difference is that this index can tell you one phase from the other. So whichever you want to call topological, you can call topological, and the other one is trivial. But basically, what it tells you is that the two phases cannot be adiabatically continued to one another. The phase with even fermion parity and with odd fermion parity. So obviously, you can kind of see that there's a connection between phase transitions in superconductors, change in fermion parity, and this Pfaffian. However, this Pfaffian has a fundamental fault. First of all, it's written down in a non-interacting basis, so it's a single particle basis. So it uses really the Hamiltonian matrix. This is the Hamiltonian matrix of the non-interacting single particle first quantized Hamiltonian matrix. And once you introduce interactions, you don't know how to generalize this. I'm going to tell you how to generalize this when you introduce interactions in 1D. Okay, So, any questions? 'Cause I'm gonna. How does it occur?
Yeah.
So it occurs by changing the magnetic field, as I said here. You change the magnetic field. When the magnetic field is lower than the chemical potential, the site has 2 electrons on it. When it's higher than the chemical potential, then the site just has 1 down electron on it, because it gains energy by orienting it in the magnetic field. So there's a fermion parity change. That's a good quantum number. So if you've got a change in quantum numbers, you have to go through a phase transition. So basically, you've got the single particle levels crossing, or if you want to talk in many body language, you've got the 2 occupied state on one side crossing with a singly occupied state on one side. They just cross in energy. Does that?
This example, you need delta.
Huh?
This example, you need the pairing to phase transition happens even in.
The phase transition happens the phase transition happens even without the pairing. This is kind of like an example of like what Oshikawa was talking about, right, in the Dresden conference. It's a trivial thing. It's like I occupy 10 bands, and then I occupy 1 band, or I occupy 1 singly, because I have particle number, even without delta. So even without delta it happens. I just have particle number, and that's what protects it without delta. Right? So, but yeah, very good. Okay, so now what did I want to do? Okay, I wanted to go to the 1D problem.
I have a question.
Yes.
Example, is it an anomaly? You change the number of particles
Well, you change the number of particles by tuning a magnetic field. I mean, I wouldn't call it an anomaly. I haven't introduced any flux to the system, or I haven't done any. It's kind of a trivial in it's a 0-dimensional. I don't know if there's any anomalies in 0 dimensions. Somebody can. I don't think there are. But so that's a good question. In higher dimensions, certainly you get anomalies, but those you describe them by, response to some flux insertion or some other things. I want to go to 1 dimension. Okay? So now let me go to 1 dimension, and let me get rid of spin. I want to get rid of spin. I want to do spinless, but I still want charge conjugation squared to equal to 1. Okay? So now what I want to do is I want to write down a 1-body Hamiltonian. And this 1-body Hamiltonian, I'm going to write it down as p squared minus mu. And this is C dagger P CP. And I'm going to write down a pairing term. And this pairing term, can I write this down? Can I have an S wave? And this is the reason why, if you just have a purely ferromagnetic state with infinite exchange coupling, you can't get S-wave pairing. But of course, you have spin-orbit coupling and other things that you learn about in Felix's talk. You can. Okay, so I can't do this because if I switch, I get a minus sign and I kill it. But obviously, I can do something that's antisymmetric, P, right? So I can do this. Is that clear? Okay, right. Okay, so now this Hamiltonian, if I write it down in, psi p, which is CP, C minus P dagger, okay, this Hamiltonian looks like this. Delta, delta star. Okay. So it already should ring some bells, and I'm not going to do it here because I think Phil is going to do it. But it should already ring some bells that this has some topology in it. But I'm going to show you that it's got some topology by... what's that? Yeah. Damn you, Ilya. Okay, so good. So the way I want to present that this has topology in it is through a flux insertion argument. And this really will get you to learn more than just the Pfaffian. Okay? And if you compute you can put it on a lattice, which will give you the Kitaev model, which I don't know if I'll do, but I might skip it. So you can put it on a lattice, which will give you the Kitaev P-wave wire, and then you can compute this Pfaffian, and it's going to have some topological state and non-topological state. But the real way that I want to think of it is if I, generically, if I add interactions and other things, what is the property of this Hamiltonian that makes it topological? And the way to think about it, at least the way I like to think about it, is the following. By the way, anybody has any guess on when this would be topological? For what values of mu? Positive or negative? Okay? So let's see why. So again, I'm going to work in delta very small limit. So work in delta small, by which I mean much smaller than mu. Okay? The band structure of the original thing looks like this. Okay? And this is energy. This is momentum. This is p squared minus 2m. If the chemical potential is here, you just do another band and you open a gap. Yeah? Like we learned. Am I making sense here, or yeah? Is this too slow? Okay. All right. So what I'm really going to do is I don't want to work on this Hamiltonian in the continuum, really. So what I'm going to do is I'm going to discretize the values of the momentum. So put a number of sites n. Say n is even. And discretize the momentum. So I'm going to take values pi, which is I'm going to put periodic boundary conditions on it. 2 pi over n times I. This is periodic boundary conditions, right? So then what does this do? So this is momentum 0. Well, I have a state at momentum 0. I have a state at, this is p in units of 2 pi over n. 1, minus 1, 2, minus 2, 3, minus 3, 4, minus 4. And is the envelope of this guy. Okay? This envelope is just, if I solve it on a computer, I just have discrete levels. Yeah? Okay. So now, let me do the same, but, so this is periodic boundary conditions. Right? So P is equal, Pi is equal to 2 pi I over n. So now I want to do the same, but I want to do it with anti-periodic boundary conditions. So with anti-periodic boundary conditions, what is Pi? What are the values of the momenta allowed? Come on. Huh? We agree? Yeah? Okay. So what has happened to this spectrum as I make it with anti-periodic boundary conditions? Whatever you want. Let's do 2 pi over. Okay, well, what happened to it is that I've moved these by a half here and here. Right? Is it obvious that this levels? So I still have the same envelope in the continuum limit, but now this state at 0 is not occupied. I have these things, where this is just in the middle of this, right? I've just shifted the momentum. And this is in the middle of this. And this is in the middle of... Sorry, this... Fuck. This is here. I guess I shouldn't swear on camera. This is here. Okay, right? Agreed? So what have I done? Well, I've changed the boundary conditions. Okay? And I've just written 2 spectra. So basically the point that I'm trying to make here is I'm trying to give you a very overarching reason why single band in 1D is topological, without any models, without any real, explicit models. Okay, well, what happens? What have I done? I've just changed the periodic to anti-periodic boundary condition. How can I actually do that in a system? Well, if I put my system on a ring, the way I do that is by inserting flux pi through the system. You agree? Because if I insert flux pi, I can just make the last link, which in periodic boundaries say I have all these links hopping t, t, t. The last link I make it minus t. And that's inserting flux pi. I can put all the flux on that link, for example. Yeah? Okay. So why flux pi is fortuitous? Well, flux pi is the only one, if I inserted some other flux, I would break, because the system breaks U1 symmetry, so the Hamiltonian would not be invariant. But flux pi, C dagger, is minus, C dagger goes into minus 1 times C dagger, so C dagger is still maintained, right? So this is basically called Z2 flux, right? Okay. And what happened to my system? So I'm again working the delta very small limits. So I'm going to work with particle number conservation, then add delta, and look at fermion parity. The only difference is, once I add small delta, I'm not going to be able to talk about particle number conservation. I'm just going to be able to talk about parity. If my chemical potential is here, what's the particle number in both cases? So say with periodic and anti-periodic boundary conditions. Does it change the particle number as I insert flux pi? Okay. So when mu is minus infinity, the fermion parity, so call it fermion parity for periodic boundary conditions, and the fermion parity for anti-periodic boundary conditions is the same. So their product is 1. Yeah? Okay. Now let me put my chemical potential here and make these things, make this level spacing large, for example, if you want. Just take it. That's not going to matter because I have a gap in the system once I put delta on, right? So let me put my potential there. Now what happens, okay? What happens to the particle number with periodic and anti-periodic boundary conditions? It's what? Changes by 1. The fermion parity, so when mu is positive, the fermion parity with periodic boundary conditions times the fermion parity with anti-periodic boundary conditions is equal to minus 1. Okay? So now, there's obviously something very important about it. It just means that threading flux through the system changes the fermion parity. Okay? How can that happen? This guy is an insulator. Right? Okay. So this is very common. This does nothing. How can it happen? This guy is an insulator. Well, there's a very simple way that it can happen. And the way that it can happen is if this insulator has edge states when I don't put periodic boundary conditions, but I open the boundary. Right? So I claim that under some circumstances, this thing, you can make it happen. Instead of doing this, I now open the system. Okay? Open boundary conditions. And if I have a Majorana edge state localized here, and a Majorana edge state localized here, call it gamma 1 and gamma L. Yeah? So if I just have edge states which are localized there, then I'm going to try to connect the system between them. And the way I connect them is I times the hopping times gamma 1 times gamma L. Yes? I just form a combination of this and this operator. And this is for what? For periodic or anti-periodic boundary conditions. So this is for periodic boundary conditions. What is for anti-periodic boundary conditions? Okay. Now, what are the ground states of these two systems? Well, I can make a complex fermion C is equal to gamma 1 plus I gamma L over 2. And then I claim that the Hamiltonian I T plus minus T gamma 1 gamma 2, you can go through, or gamma 1 gamma L, you can go through it. It's a very simple one-body calculation. I claim that this Hamiltonian is is plus minus T C dagger C minus 1/2. And it's got to be C dagger C minus 1/2 because it's particle hole symmetric. So singly occupied and non-occupied at energy have to be an energy plus and minus. Yeah? Makes everybody following? Okay. So now plus and minus is periodic or anti-periodic. Now is it clear that the ground state of the system for periodic and anti-periodic changes parity? Okay? So the easiest way to see that you have edge states is to first see that inserting flux pi, if you've got chemical potential larger than here, larger than 0, gives you a change in fermion number with open and closed with periodic and anti-periodic boundary conditions. And the one way that can happen under some assumptions of locality, etc., is by having edge modes, Majorana edge modes, which when you connect now, if you connect them through periodic or anti-periodic boundary conditions, they have different fermion parity. Okay? So what are the so basically you can propose, so what are the advantages? So the topological index, I claim, is and this is basically an anomaly, is the product of fermion parity with periodic and anti-periodic boundary conditions. And if this is minus 1, so if as you insert flux, the system goes between even fermion number and odd fermion number, then you've got a topological phase, and you've got end Majorana end modes on it. Okay? Why is this important? Well, first of all, you can solve the Kitaev model, which I don't think I'll have. How many people know the Kitaev model? Because I don't think I'll have. Okay, so I'm not going to go through it. But it's, for people who don't know the Kitaev model, there's notes that I can give you, and I think Felix will go through the Kitaev model. But the point is, the Kitaev model has an index, which is a Pfaffian index, which is a single particle index because it uses a single particle Hamiltonian. It's also an index that doesn't actually work in the full. It works with even if you put the system with on an even number of sites. You put it on an odd number of sites and with different boundary conditions, it doesn't work. So, but the real index of these insulators is really this anomalous response. And this anomalous response works even if you add interactions. So this I put a band here, but now I can add interactions. And if I add interactions, I'm just going to have a system, diagonalize it, have a Hamiltonian, write it down on a many-body basis, diagonalize it in two cases, with periodic and anti-periodic boundary conditions. I look at the ground state, and I can immediately compute the fermion parity on the ground state. And the fermion parity on the ground state will change if the system is topological. Okay? So this is the index, this is the interacting index. And you can prove this through matrix product space that I won't get into it. And actually you can generalize this to parafermions, so this is something that we're trying to do now. But I'm not going to get into that. Okay, is that clear? Okay, and is it clear that these had to be Majoranas here? Okay.
That is if you identify the site 1 and site L.
Well, identify site. I'm just going to make this.
So you don't add a hopping from site 1 to site L.
So open boundary conditions, I don't add a hopping, but periodic boundary conditions, I'm going to add a hopping.
So then this C dagger C, where is it?
Which C dagger C?
So that's C. The C you define by 1 gamma 1.
So the bulk of this is, so what's, very good. So what's the spectrum of that model? It's just like the spectrum of the Kitaev model. the bulk, the single particle spectrum, the bulk is gapped. Okay? So I'm not going to worry about what happens in the bulk. But the edge is gapless. I have Majorana gamma 1 and Majorana gamma L. There's maybe some exponential splitting between them. Okay? So now I'm going to ask, how do I introduce periodic and anti-periodic boundary conditions? I'm not going to worry about the bulk since it's gapped. I mean, there's issues with that. To actually prove this, you need to do like quasi-adiabatic continuity, etc. But the gist of the issue is that I'm just going to worry about the zero modes here. So I'm going to add a coupling between them because I wrap the system around. I don't let this be like this. I wrap the system around. I'm going to add a coupling between them, plus or minus t. Okay? And see that if I add plus, so I'm just going to work in the basis of these modes, which are just the low energy modes. So I've got rid of all this shit. So in the basis of these modes, the Hamiltonian with this C is just T, C dagger, C minus 1/2. So depending on whether this is plus T, if this is plus T, if this is periodic, the ground state is unoccupied, because this is minus, imagine T positive, right? If this is minus, the ground state is occupied in this C fermion operator. So it changes fermion number. It changes fermion parity.
So I guess my question is, where does this fermion live?
Oh, well, if I have open boundary conditions, it's obviously a superposition between gamma 1 and gamma L. So it's delocalized. And that's what makes these chains very, the Kitaev chain topological. If I add this order here, I won't be able to live the degeneracy because the fermion is highly delocalized. Right? This is just a construction. So basically, I've just constructed this. Nobody falls asleep, okay? I've just constructed this fermion to be able to define a Hilbert space. Normally, Majoranas don't really have a local Hilbert space if they're single. So if I had two Majoranas here, I would be able to make a local Hilbert space. But if I have one here, I can't get a local Hilbert space. So I constructed this fermion with open boundary conditions delocalized. Now, as I wrap the boundary conditions to make it periodic or anti-periodic, I bring these two together. So if I really take this thing and make it a circle, then the fermion is going to live, close to that bond. Yes?
So it's not clear to me at which point you use the fact that you have the pairing, because this parity thing works out without pairing, but then you introduce Majorana.
I've used the fact that there's got pairing to basically argue that you've got a gap in the system. This is a gap. If I didn't have a gap, the moment I introduce any T, the moment I make this periodic boundary condition, this open boundary conditions, then any splitting here would actually start mixing with these other levels. So I wouldn't be able to just focus on this low dimensional, just the two Majoranas at the end. Because I have a gap, I'm just able to focus on the two Majoranas at the end and work in that Hilbert space. Right? Does that make sense?
Maybe.
Okay, if it doesn't, just tell me. Call BS if it doesn't.
If you just look at the parabolic bands,
Yeah.
you have a small gap in there.
Yeah, but that's a finite size gap. Okay? This is 2 pi over n. With finite, as I go to large number of particles, this will vanish. Right? This, as I go to large number of sites, this will vanish. Okay? I've just given you like a, and basically, in Kitaev's chain, the change in the Pfaffian number, as I make mu go from minus infinity, there's a phase transition here in the Kitaev chain, everybody knows. And the Pfaffian number is just the fact that you've got this one state. This picks up all the Pfaffian, all the change in the Pfaffian. These contribute the same. The Kitaev chain just picks up. But if I actually do the Kitaev chain on anti-periodic, the Pfaffian won't change. So the Pfaffian is kind of an inherently flawed quantity. It's good for some, BS non-interacting systems, but it's not. It's a fundamentally flawed quantity, and the real topological index is the response of the system to flux insertion. That I've illustrated here in a non-interacting way, but you can put it on more solid ground. Okay, so I want to do yes. Yes.
If I understand correctly, the change of fermion parity is attributed to H states. However, it circle. And with that, from the reference, I'm going to P plus. If I understand correctly, the cavity of fermion will change. And
Not-
there are no edges.
No. So if I'm here, my chemical potential is here, for example, it doesn't matter what flux I put in, the fermion parity won't change. See, it's an unoccupied band. And I put it here, it's an unoccupied band. My wave function is 0 in occupation basis, 0, 0, 0. So the parity doesn't change in this case. Is that clear? So I have a band like this, and I put my chemical potential here. The wave function is just, whatever orbitals of momentum I have. So Cp, I have orbitals of angular momentum p. With p, those values or those values. My wave function is 0, 0, 0, 0, 0. It's unoccupied. And as long as the gap is not large, of course, the wave function, if I have some sort of delta, it's just going to be superpositions of this. I hit this with a Hamiltonian, I can do a perturbation theory, but the point is, it's not going to change fermion parity. As long as, the gap is not larger than this. This gap, the superconducting gap. So this is fundamental. Is it clear that if I'm here, I insert flux pi, I don't change anything? Okay, so what I wanted to do now, so we started late, so...
Can I ask one more?
Yes, of course.
You have this picture of the bands and these two levels coming close to 0. So these levels are for fermions, right? Not Majoranas, but they are fermionic levels.
These are, they have a fermionic, they have a representation, yeah. This level and this level, they're related by particle hole, by charge conjugation.
Okay, so it seemed to me that when I put this level to be degenerate,
Which
I
levels?
just have a doubly degenerate fermionic level.
These? Which levels?
The lowest level.
These ones?
Yeah.
Yeah? So you put them to be degenerate, but they're Majoranas. I have gamma 1 and gamma L. There's two levels, but... So if I diagonalize as I wrote down that Hamiltonian matrix, right? It's a 4 by 4 matrix or whatever. Here is going to be, 2n times by 2n, where n is the number of sites in the system. I diagonalize that matrix, and I get a set of eigenvalues. And that's a first quantized, non-interacting picture. And then I get these eigenvalues at 0 with open boundary conditions, if the system is topological. But if I go back and ask, how do these what is the form of the operator that creates these eigenvalues, then I need to introduce this psi. And you'll see that it's an exact superposition of particle and hole. So this Majorana is, and this is actually, at what time is my talk tomorrow, before yours, Felix, or after? Okay, can we switch? Okay, so then you'll see the Kitaev, you'll see this in Felix's talk very explicitly.
So it's this.
Thank you. Sorry, yeah.
So you're saying that it's the redundancy in this picture that makes me able to write the levels in terms of 2 Majoranas, not 4.
Well, so there's so there's no 4 levels. With open boundary conditions, when you diagonalize your system, you're just going to get a set of numbers.
Yeah, but you're saying that...
And you're going to get 2 numbers very close to 0. Okay?
They are related to each other by particle hole.
No. Well, this particle hole with open boundary conditions, particle hole, you can form a superposition of them, but particle hole is a local symmetry. So in other words, it doesn't change 1 to L. Okay? So if I work with a Majorana that's purely localized here, then this is its own particle hole conjugate. So in other words, if I was to write this down, as you'll see tomorrow, as some function of the C on the site 1, this would be C1 plus C1 dagger. this would be gamma 1. And you notice that this gamma 1 dagger is equal to gamma 1. Okay? And gamma L would be CL plus CL dagger. Okay? Now I can, so okay, does that answer your question?
I think so.
Okay. So I was going to do like the example of, I was going to couple Kitaev chains and put a symmetry on them and do an example of an SPT, but I think I'm going to do that tomorrow.
One more question.
Yeah.
Yeah, so if you're at zero energy, then this, so zero energy state, this particle Hall conjugacy can take a thing to itself then. So is it possible for a thing to be its own particle Hall conjugate?
That is the Majorana.
Okay, sure.
That is exactly what the Majorana is its own particle Hall conjugate. Of course, if you're far away from zero energy, if you're like a little bit, then particle conjugacy sends this into this, right? But if I really have no splitting between these two Majoranas, okay, then particle Hall conjugacy acts here, sends this gamma 1 to itself and gamma L into itself. Okay, they're their own antiparticle, right? And this you can clearly see because I have, this psi of P is, C of P, C dagger of minus P. So everything is going to be a linear combination of these two. If I have momentum, if I have open boundary conditions, I don't have momentum, but I'll still be able to write down some of the C and C dagger. And you can solve for the actual, you have a Hamiltonian, which is 2n by 2n sites. If I have an n number of sites, you solve it, you get a number of eigenstates. You look at these two eigenstates here, and you see they have equal superposition, equal weight on C1 in a certain dimerized limit. Okay? But that's a model. But to go away from models and make this more relevant, just think of inserting flux and coupling these Majoranas through. Okay, yes?
And this shows that you always have two Majoranas. You cannot have one.
Well, you can't. There's no way you can have. So this is preempts the vortex discussion that we're going to have. There's no way you can have just one Majorana here for several reasons. Okay? So reason number one, my Hamiltonian. So these levels here, again, these energy levels, are just diagonalizations. You plug a matrix, a Hamiltonian on a computer, and you diagonalize it. My Hamiltonian's got even dimension. Because any superconducting Hamiltonian, I just double it. So it's got even dimension. If I just said 1 here, it'll be odd. There's no way of just getting 1. Okay? And so you just get 2, but one of them is localized at one end of the sample, the other one is at the other end. And that's actually crucial for this argument to the flux insertion to work, because if they weren't localized here, as I would close the boundary conditions, if they're localized here, close the boundary conditions here, nothing would happen. But if they're localized here, if I close the boundary conditions, they can hybridize. All right, yeah.
Since each particle is its own antiparticle, then does that mean that they should not have charge?
Well, charge is kind of like a, not well-defined concept because I've got a superconductor, so I don't, particle number is not a well-defined concept. So they've got, their combination, the 1 and L, the one at, the Majorana at 1 and Majorana at L, their combination creates a fermion, an actual complex fermion, a legitimate complex fermion. Now this fermion is nothing but kind of like some sort of a, trick to create a Hilbert space. So notice that if I just have this Hamiltonian, how do you diagonalize this Hamiltonian? Well, usually the way you diagonalize a Hamiltonian is you just pick a basis of states, you write your matrix, and you diagonalize it. If I just have this Hamiltonian, what would you do? I can't build a Hilbert space for a single Majorana. So what I do is I write down this complex Majorana, this is complex operators localized, and now I have a Hilbert space, which is 0, such as C times 0. 0 is defined by the property that C times 0 is equal to 0. And 1, which is C dagger 0. And now I can diagonalize, I have a 2 by 2 Hamiltonian. And if I diagonalize this particular one has got energies minus 1/2 and plus 1/2. And if it flips the boundary conditions, you exactly flip them. So you flip the fermion parity of the ground state. Is that clear? All right, any other questions?
What happens if the bands have no dispersion?
If they, if the bands have no dispersion, then you're, you've got a highly degenerate set of states, and basically, you need interactions to do anything. So you need to have some dispersion. I mean, it's the same question. It's the same question as what happens, same questions of what's a flat band metal. Not very much. You need interactions to, So we all learned of the concept of Fermi surfaces, right? What happens if my band is like this? Where's the Fermi surface? You don't have a Fermi surface in the non-interacting limit. You just have a set of degenerate states, and you need interactions to lift that degeneracy. Does that make sense? So just think of them. So basically, that's a highly pathological case that I don't want to wrap my head around. Yes?
You mentioned that if you diagonalize the system, you get to the degenerate or close to degenerate states, and if you map it to the operator or ask what operator creates it, then it's a Meyer.
Yeah.
How do you ask this question? You get the spectrum. How do you map it to that operator that creates it?
Oh, so that's a very good question. So actually,
He was a really good question. Could you rephrase it because we didn't hear it?
So the question is, when I solve the Hamiltonian, how do I see that this guy is an equal superposition of these things, right? And actually, I certainly encourage everyone, rather than drinking at night, to diagonalize this Hamiltonian and leave me with all the beer. And so the way you do it is you just plug in that matrix, okay? And you've got a matrix here, like a 2n by 2n matrix, where n is number of sites, okay? And here you've got a spinner, so this is a matrix, it's just a set of numbers. This is operator. So this is, gamma 1, C1 dagger, C2 dagger. These are operators on each site. C3 dagger, etc. All right, you forget about this. You just plug in this matrix. You type eigensystem in your Mathematica. Out pops some eigenvalues. You look at the zero energy eigenvalue. In the dimerized cases, in fact, if it's not fully dimerized, it will spit out a linear combination of them. But in any case, so let's just talk in some special case, you look at the eigenvalue at 0. That eigenvalue has an eigenvector associated with it. You pull it out from the Mathematica, and that eigenvector will have 1, 1, for example. And 0, 0, 0, 0. Okay? So that's how it's going to basically work. It's very silly. Just take, just take, leave the beer, grab the computer, and just diagonalize this, and it's very easy. Okay, any other questions? Yes?
What's your ground state degeneracy when you have periodic boundary conditions? Again, the thermodynamic. Is it twofold degenerate?
No, it's periodic boundary conditions. All these are insulators. It's singly degenerate. I mean, all these are insulators. All these are band superconductors. So that's a good point. So these are states. Yeah. So basically, so with open boundary conditions, the ground state is twofold degenerate, right? Because I have out of the Majoranas 1 and 2, 1 and L, I can build this operator C. And if I don't have any hybridization between them, so open boundary conditions, then the state 0, that one, and the state C dagger 0 are degenerate. Right? Is that clear? So that's with open boundary conditions, a twofold degeneracy. With periodic boundary conditions, I just wrap these around, and even this simple argument tells you that I'll pick one state at energy minus 1 times T, where T is D. Is that clear? Yeah? So it's singly degenerate when you close boundary conditions, doubly degenerate, or more than one-fold degenerate, which gives you the fact that you have these degrees of freedom when there's questions. I've stopped. Don't worry, I stopped. Am I getting paid? Is this like that's very new. Well, thank you, Claudio. Now that you've offered. Okay, does that make sense? Okay, any other questions? No? All right, well, thanks.